that I would concentrate on forced turbulence simulation. And most of the slides I'm going to show are overlapped with those I presented at the second workshop in September. So, thank you. Is this okay? Also, thank you for heckling me. Okay, so these are, first I'd like to mention something about transition in energy spectrum for rotating and stratified turbulence. These pictures show, appeared several times in this conference, but this is a famous Nastrom gauge atmospheric observation, and well, Peter showed some criticism, but anyway, clear transition from -3 to -5 and this is one which Mark Taylor and NCAR's group, including Joe Trivia, presented. So the spectrum which showed -3 and -5 but these two are, well, actually, -3 is explained as an entropy cascade for quasi-geostrophic turbulence, so it's more like 2D, and while -5 is Kolmogorov turbulence, and the energy transfer is forward, which was tested by Lindborg. And so, but the problem is when there's no rotation, so pure stratification case. And so these are summary of observations, theory, and simulations. First observations, the KZ spectrum, the vertical spectrum is -2 or -3 to Kolmogorov spectrum, which was presented by Monk, Garrett. And transition wave number, they presented with the Ozmidov scale. And theory also support all Ozmidov scale for transition by Monk, Garrett, Lamley, and Holloway. And simulations are given some people, George Cannavali, Briscolini, and Orlandi used LES with 128 cubic simulation. And later Yoshida, Ishihara, Kaneda used the 512 cubic with LES. And they, well, supported similar to Ozmidov for transition. And well, Waite and Bartero did some DNS with hyperviscosity. And please look at Waite and Bartero for the review. And the objectives of my talk today is first to investigate the transition of energy spectra for not rotating stratified turbulence by using full DNS with 1024 cubic grid points. And to characterize each spectrum with proper scaling and to understand anisotropic features of stratified turbulence. So this is a Navier-Stokes equation with Buzynski approximation. So I can skip, I can show a few things about. So we put the Brandt-Weissel frequency here, and which is a mean gradient. Anyway, so and the numerical method are summarized like this. We forced, so these are forced simulations results. And 2 pi periodic packs with 1024 cubic grid points, and microscale Reynolds number is around 300. And we use a third order time matching scheme, and the initial energy spectrum is 0. So everything is, well, energy is accumulated by forcing to form some nice spectrum. And we force only horizontal velocity components. By adding red noise, which means solving some kind of stochastic differential equations to modes within the wave number band. Wave number band in particular for this case is 5, so it's a rather large scale. So, well, before showing our result, let me summarize some characteristics of stratified turbulence. And first, stratified turbulence is a composite of waves and turbulence. So we need to deal waves and turbulence or vortices separately and by using Cryer-Herring decomposition to separate these things. I will explain Cryer-Herring decomposition later. And so another characteristics of stratified turbulence is highly anisotropic. So we need suitable averaging. And so we divide the k-space wave number into horizontal and vertical. And horizontal for vertical, well, actually for horizontal wave number, we average inside the cylindrical shell, while for vertical wave number, we average inside the planar plane. So Cryer-Herring decomposition is, it's also called the toroidal and poloidal decomposition. The idea is incompressibility is equal to k dot u in Fourier space equals 0. So u tilde is spanned by two independent vectors perpendicular to k. So we use two orthonormal vectors which is perpendicular to k by taking vector product. So using Cartesian coordinate, so these unit vectors can be expressed like this. And the third component is k, wave number itself. So these three makes orthonormal coordinates. So if we decompose velocity, Fourier component of velocity using E1 and E2, the coefficient of E1 component is by taking the dot product with u with this unit vector, which is calculated explicitly to give omega z. Sorry, I forgot to put z. So omega z is a third component of vorticity. So that's why phi1 or the coefficient of first mode is called vortical. And meanwhile, the second component, the second coefficient is calculated similar way, and to give, this is w, which is the third component of velocity. And third component of velocity is coupled with temperature fluctuation and gives a wave features of turbulence. So that's why the phi2 is called wavy vector, wavy component. One of the nice things about Cryer-Herring decomposition is if we have linearized the Navier-Stokes equation in Fourier space and substitute decomposition u, k, and theta into these, and the equation can be actually transferred, or actually decomposed into phi1, phi2, phi2, phi3, like this linear matrix equation. So by checking the wave eigenvalues and eigenvectors, velocity field can be decomposed into eigenmodes. So that's here, of course, omega is a rotation, which we don't have today's talk. So only two components, phi2 and phi3, are coupled with n, where c is the angle between wave vector and z. Okay, so here's a result of our simulation. And first, the history of total kinetic energy. As I said, at t equals 0, everything is 0. And energy is accumulated to have some peak and then becomes stationary. So for example, n square equal 1 and 10 and 50 and 100 are shown. And this is the final time. And at that time, microscale Reynolds number is around 300 to 400. Okay. And this is history, where actually history of phi1 energy spectra. Phi1 is, as I said, it's a wave, vortices, horizontal energy spectra when n square equals 0, n square equals 100. And so I accumulated all energy spectra, development of energy spectra. So at t equals 0, it's 0, but it goes, as energy goes up, so we see the development of energy spectra. And the marked time, it's a 7, is we see very straight, steep energy spectra. And at the marked, this one is a 10, so we see that some part, some small scale part raise. And at that time 13, so it's fully developed and becomes stationary. So please remember this pink zone, 7 from time 7 to 13. And inside this pink zone time, so energy, where energy spectrum is, or transition in energy spectrum is developed. So first, the summary is first steep spectrum, like K2 minus 3 or minus 4 develops, then small scale rise. So this is a summary of or accumulation of the last spectra for various stratification, n square equal 1, and n square equal 10, and n square 50, and 100. And clearly we see some minus 3 spectra for all of them, and minus 5/3 spectra for different lines, curves for different stratification. So minus 5/3 for small scales, different coefficient, while minus 3 for large scales, but same coefficient. And there's a sharp transition, and the problem is how to scale them. And we employed these guidelines. First, the Kolmogorov constant is universal, even for isotropic subset of anisotropic flows. That is a point. And the coefficient for, meanwhile, the coefficient for large scale doesn't depend on n. So encourage.
Constant based on the 3D spectrum or 2D?
2D.
Horizontal.
2D horizontal.
Yeah, okay,
yes.
that makes sense.
Yes. And encouraged by, well, stimulated by Peter Bartero's talk, so I, removed the guideline and show even without the guideline, we see some, sharp transition in these spectra. So here's the proposed scaling for phi1 horizontal spectra, horizontal energy and horizontal wave number. And energy spectra is for some critical, smaller than critical value, Kc, it shows minus 3, but the coefficient is parameterized by horizontal entropy dissipation. So K per power 4 and E phi1 energy. And while for the higher wave number part, small scales, so Kolmogorov type scaling, but the energy dissipation is should be calculated by horizontal energy dissipation. Oops. So the reason we propose these spectra is something like this. Here's and compensate the spectra using IUTA entropy dissipation. Horizontal entropy dissipation gives a nice collapsed value for large scale. And for using for small scales, using Kolmogorov epsilon or horizontal dissipation of horizontal energy or vortex energy gives a nice value of Kolmogorov constant between 1.0 to 2.0. So using these values, alpha is 0.02 from the fitting in the previous slide, and ck as a Kolmogorov constant. We can calculate the transition wave number kc as alpha over ck 3/4 and times some ratio of entropy dissipation over energy dissipation, but they are horizontal. And by using the numbers, we can calculate the transition of wave numbers, something like that, 11.8.89, 10.66, and 8.54, blah, blah, blah. So it gives some, they give some nice reasonable transition wave numbers. So for other spectra, so this is a wave energy as function of horizontal wave number gives -2 and for large scale and -5/3 for small scales. And with the same manner, we can calculate the transition wave number something like this. So the transition wave number is proportional to the Ozmidov-like scale, but the Ozmidov, well, so Ozmidov scale is something like this, but here the energy dissipation is based on horizontal dissipation. Well, for small stratification, for small n's, the transition is very small, so we couldn't see. We can't detect the transition. But for very high stratification, the transition may appear. Okay, so for other spectra, in particular the vertical spectra of vortex and vertical spectra of waves. So we see, some mixed result, -2 and -3. And in particular, we are interested in the wave spectra in the vertical energy wave number. So -2 is maybe explained as Garrett-Monk spectrum, and with some transition to -5/3, but we don't know. And -3 is perhaps explained as a saturation spectrum by Peter Bartero or many people. And this is some blow up using a compensated spectra for various wave stratification. And well, actually it gives 0.1 n square kz -3, but not the flat, but only touches or tangent to that spectrum. And so there might be some most unstable wave number, which may give some length scale in the vertical direction, but we don't know yet. So, and this -0.1 is by Joel Someria? Yeah, so, or Chantal, I don't know.
We got this result, but in 2 dimensions.
Okay.
In 3 dimensions, I think the 0.2 coefficient is right. We can discuss about that later.
Okay. So, well, we have presented some idea of anisotropy in dissipation. And the 3D total dissipation can be decomposed into horizontal and vertical using wave and vortex and waves into this. And we have 4 different energy dissipation. And these 2 are horizontal dissipation, and these latter 2 are vertical dissipation. And these are final value of dissipations. And I'd like to point out for horizontal dissipation becomes smaller and smaller for stronger stratification. But for vertical dissipation is a little peculiar. So the dissipation becomes stationary, almost stationary for the phi2 is a wave energy in the vertical way. but the most interesting thing is this quantity, which is dissipation of horizontal energy in the direction of vertical direction. And so actually, if stratification goes bigger, the dissipation becomes bigger. And actually, this dissipation is related to the vertical shear of the horizontal wave component, velocity component, and which is local Richardson number something. So local Richardson number is determined by such kind of dissipation. And if we look at the vertical phi1 dissipation spectra, so we see, so this is the dissipation spectra. And first, the large scale have more dissipation for higher stratification. So we see more stronger dissipation for higher stratification, or stronger stratification, which may be related to so-called zigzag instability by Biram and Schomerz. And small scale scales have similar dissipation for all stratification. Okay. So last time in September, when I presented these results, Eric Lindborg asked me about buoyancy Reynolds number. And since then I calculated and I would like to show some result. And so this buoyancy Reynolds number, which is given as a fluid number, horizontal fluid number square Reynolds number, and given as a epsilon over nu n squared. And by Blesswater and Biram, Lindborg, and Schomerz, if buoyancy Reynolds number is smaller than 1, we expect a steep spectrum, and when R is bigger than 1, we may have minus 5/3. So I checked the value of R for various Brandt-Weissler frequencies, and so interesting thing is it goes up quickly after the energy takes the maximum value. So all those numbers are, of course, bigger than 1, and even for n squared equal 100, very stable, strong stratification, we have a bigger number than 1. And if we grow up the last slide for buoyancy Reynolds number for n squared equal 100, so this is a curve as function of time. And so here, epsilon is a three-dimensional energy dissipation. But as I said, because of the anisotropy, epsilon can be divided into 4 different kinds. So still, the vertical dissipation of horizontal or vortex energy has a maximum contribution to this number. And if we superpose the energy spectra, how energy spectra developed. So again, this pink zone appears, and here 7 is something like this here, and 10 is almost the time when R becomes 1, and 13 becomes is almost a maximum buoyancy Reynolds number. So inside this time zone from 7 to 13, as I said before, energy develops minus 5/3, or transition develops for a horizontal energy spectrum. So, well, maybe I don't have time for sure, but anyway, let me show. So this is entropy contours for 512 cubic simulation, and we are looking at from the side. So first there's nothing, but soon three-dimensional object appears, and then they began to migrate in the horizontal direction. So this is a side view.
Looks rather zigzag, doesn't it?
Yeah. And so next slide is so this we see some oblique direction or angle view.
From above.
From a little, yes, from above, yes. So pancakes first appears, so which may give some steep spectrum, but then we see some wiggles or wrinkles on the surface of pancakes. Those are the explanation of -5/3 or three-dimensional spectrum.
KH presumably.
Yeah. So we see many, streaks, so which may be related to KH.
Yeah.
Okay, so the summary is energy spectra. Energy spectra investigated for stably stratified turbulence with 1024 cubic pseudospectral DNS simulations. Horizontal spectra show a clear transition from 2D to 3D Kolmogorov spectra. And horizontal spectra are scaled by an isotropic dissipation of energy and entropy, and pointed out an isotropy in the energy dissipation for stratified turbulence. And the last thing is buoyancy Reynolds number bigger than 1 seems a condition for the transition to appear. Thank you very much.
Can we go back to the horizontal spectrum scaled by epsilon to the 2/3 k to the minus 5? The reason I'm asking is I'm not sure what you said about it.
This one? Or
But well, the results,
result?
the horizontal spectrum.
Horizontal spectrum, okay.
You had one that was compensated by epsilon to the
okay.
2/3 k to the minus 5.
This one? Or
One more
compensated?
later.
Compensated, yes. Yes.
That's the one.
Yeah.
So what did you say about that? Is it? So I guess I'm talking about the graph on the right.
This one?
No, on the right.
Yeah.
That's compensated by.
Compensated by epsilon, but the epsilon is horizontal dissipation of phi1 energy.
And it's the phi1 spectrum.
Phi1 spectrum, yes.
Okay, so does that mean, are you saying that that scales, or are you saying that doesn't scale?
I think it scales, yes, because of some discrepancies, but it gives some reasonable value for Kolmogorov constant, three-dimensional Kolmogorov constant near 1.5.
I mean, I guess beauty is in the eye of the beholder, but when I look at that, I see that it's logarithmic and,
Yeah?
I don't know, about 7 or 8 orders of magnitude. It doesn't look like it scales very well to me.
Okay.
And if it doesn't, that means that what Riley and Lindbergh are telling us about that spectrum being independent of the stratification is, it seems to me that you're in somewhat mild disagreement with that.
Yeah.
It also looks like that where you have your flat line fitted, that's the least stratification. As you go up in stratification, as you go down, what he's talking about gets worse.
The slope looks like it's different too, not only the amplitude.
Okay. I tested many different, epsilons, and so this is best possible candidate. That's why, yeah.
So something like -5/3 plus or minus a third, I suppose.
That's cheating.
Can
I don't-
ask a related question? Because this is supposed to be a combination of two spectra, right? Two different power laws. And each coefficient depends on an integral over all the case.
Mhm.
So why your ansatz for the energy spectrum has two parts? For me, it should have a linear combination of two power laws. Can you comment on that?
Linear combination, that's what Michael told me. Well, so linear combination of -3 and -5/3.
Yeah, that would be because you're using to compute the coefficient. You're using all the case.
Yeah.
So why one coefficient
Yeah.
appears only in one?
Yeah, I think I tested by subtracting, -3 spectrum or -3 energy from this and try to fit. But
Oh, yes, I think that transition that he's talking about now is rather smooth if you do what you suggest. It goes, very gradually, whereas these transitions are rather sharp. So you have to have a different way of explaining it, I think.
Right. Okay, let's move.